Hello, do you hear me?
Hello, good morning. We are going to start shortly.
Okay.
Okay, good morning once again. For some reason, there are only four of us, but we probably have to start. Okay, so yesterday we discussed, I think, the main families and some history milestones of modern operating systems development. Obviously, we didn't cover the whole history. We did not start in 1950s, 1960s. We started with the advent of modern operating systems, very largely in use today. We didn't cover some important families. So, for example, the IBM family of operating systems, which has its own interesting history, which at some point used to be absolutely dominant in the markets, but much less important now, where the world is ruled by, in general, by Unix and Mach derived operating systems. Almost everything we are currently using is one way or another derived from these two very important families, from Unix and Mach, with some ideas and sometimes elements from Minix and possibly other systems. So Unix and Mach are most important operating systems of today. Interestingly, that's what I actually wanted to mention in connection with Windows operating system uh, partisans. Let me let me call it that way. Is that Windows is no longer Windows as it used to be in the past. I'm just trying to
What
check.
has changed?
Yeah.
What has changed for Windows?
Sorry, what did you say?
What has changed for the Windows?
Oh, a lot. And that is very much due to this BSD license. You remember this BSD Unixes or Unices, Berkeley system distribution, which allows absolutely free, almost absolutely free use of Berkeley system of BSD, uh, which means you can and you can't do that under GPL. Linux is GPL governed. You can incorporate portions of BSD operating system even into commercial, non-free, non-open source operating system. So basically the BSD license tells you do whatever you want, only the governors of the University of California at Berkeley will not be responsible for what you are doing. So, if you incorporated parts of BSD code into another operating system, and there was a critical failure in that operating system, and that resulted in a nuclear disaster, and that resulted in billions and billions and billions of dollars of damage, don't blame Berkeley for that. Blame yourself. So that's basically the idea of Berkeley system distribution. And at some point, you remember, okay, if we are talking about Windows, I don't like Windows, but let's talk a little bit about Windows timeline. Um, First was Windows NT. Uh, and I think the first remarkable version, I don't even remember whether there was anything before that, was 3.5 and then 4.0. And in general, Windows NT has been around since about same time as Linux. So the advent of Windows NT came around, uh, I really don't remember what there were versions prior to 3.5, around 1991, something like that. And 4.0 came around in mid 90s. I'm not talking about other Windows family derivatives like Windows 95, 98, which are basically extended versions of original DOS ported to a 32-bit environment and with a graphical user interface. They are much less interesting from our point of view simply because those systems lacked very important features, such as, for example, separation of address spaces of various processes. They run in a unified address space without offering any memory protection to the process. So that's, I would say, not a modern secure operating system by modern standards. So NT 3.5, NT 4, and then came Windows 2000, in the year 99, not exactly 2000. And then came 2 years later, in 2001, came Windows XP. And Windows XP was a tremendous success for Microsoft. So at some point, almost all, I would say, desktop solutions at some point in early 2000s were running Windows XP, where the server market was never really dominated by Windows. Various Windows Server solutions, XP, first Windows NT based, 2000 based, XP based, and so on, they did exist and they developed in parallel with the desktop versions. So these are desktop. But Windows was never a winner or the winner in the desktop in the server market. First, it was dominated by Sun Solaris and maybe other operating systems, for example, Silicon Graphics and others. Then Linux came and gradually increased its value. And currently, Mm, I think nearly all server market is captured by Linux. And by the way, all uh, mobile market, mobile devices market is nearly equally divided between Linux. Windows was trying to penetrate into the mobile market unsuccessfully, and now mobile is Android. What is Android? Android is Linux. It is a special version of Linux for mobile devices. And iOS, what is iOS? iOS is Darwin. And Darwin is, you remember the formula, Darwin is Mach plus BHD. All right? Then, after this period of great, immense popularity of Windows XP, came a relatively unsuccessful experiment with Windows Vista, and that was around 2007, if I remember correctly, which was heavily criticized primarily for not so well designed user interface. Internally, Vista was primarily a successor of XP. And then unnoticeable for many people came Windows. What came after Vista? You remember? Windows 7. All right?
I have a question.
Yes.
What is a Windows Longhorn?
Longhorn. I
Yes, because
think
I heard its name a lot, but I have never seen it.
a good point. I definitely remember the term. I think if I'm not wrong, Longhorn was a development version of Windows 7 or Windows 8. It was some kind of code project code name, which later became one of 7 or 8 mainstream distributions, something like that. We can double check that, but it was never a separate version, separate family of Windows operating systems. Let's double check. Good point. So Windows 7 was 2009, and followed by Windows 8. Then, as you remember, 9 was skipped, and we are now in a relatively successful, but still not, of course, a substitute to Linux, Windows 10 family, which was supposed to be both actually desktop, mobile, and server side, but really used as a desktop only at the moment, and even as a desktop, uh, I would say it is significantly inferior to both actually macOS and I have never been using Windows as a desktop either. So my desktop operating system, as you know, it is Linux. Many years ago, in 1990s, at some point, my desktop operating system was even FreeBSD. Uh, so what happens is Windows 7 was almost completely rewritten. In particular, what we know is that um, the whole network stack, TCP/IP implementation within Windows 7 was completely rewritten from scratch. Well, not rewritten from scratch, was completely replaced compared to the previous versions. Maybe some other components as well. So there was a heavy code influx into Windows 7. So Windows 7 was largely based upon, and now Windows 8 and 10 as successors to 7 are based upon it as well. Upon which do you think? What do you think? Which operating system was built into, to a large extent, built into the kernel of Windows 7, revitalizing the Windows family, which was about to die out already in 2007 with a hugely unsuccessful Windows Vista. So there was some significant code infusion into Windows 7 from where? What do you think?
Subsystem, Linux subsystem.
Not from Linux. From Linux you can't, because in that case, your code would need to be governed by GPL and you would need to release the sources. It was NetBSD that subsequently in Windows 10 they aim at some Linux compatibility in many senses. That is another story. And still, direct code infusion from Linux into Windows is simply not allowed legally. You can't do that. But BSD is completely free. As I say, do whatever you want, do not sue the governors of the University of California at Berkeley. And that's why Windows 7 internally had borrowed a lot of code from NetBSD. So even from that point of view, you see, even Windows is now heavily affected by the BSD family of operating systems. So really, uh, operating systems which we are currently using in one way or another are primarily Linux, Mach, and BSD, and nothing really else. So they all deserve our very close attention.
One question. So what is WSL2?
Uh, USL2, you say?
WSL2, Windows subsystem for Linux.
Yes, that's what I say. Windows subsystem for Linux. A compatibility layer. Let's explore it, and we can discuss it. Actually, many operating systems have a capability of running code from another operating system, so to have binary compatibility. So, for example, FreeBSD FreeBSD for a long time had a capability of running native Linux code. So there is a binary in a format suitable for Linux, compiled for Linux, ELF, for example, format, and FreeBSD uh, can run that code. So if this is the case, it is no surprise that Windows can also run. I presume that the technology you're talking about run native Linux code through a binary compatibility layer, because implementing that binary compatibility layer is easy. You don't need to do much about that. You can simply borrow it from FreeBSD. Again, the BSD license allows you to do that. Still, there are performance drawbacks of doing that, and I see absolutely no reason to have a Windows system, and that Windows system would run my Linux code for whatever purpose. There are many ways actually of how Linux and Unix code could be run on Windows operating system nowadays. So one of them is this direct binary compatibility. Another one you have no doubt heard about, so that's number one. Number two, you have of course heard and you are using Cygwin, right? Do you know about Cygwin?
No.
I will explain in a second. And number three, there is also a system which is called MCs min GW. So what is it all about? Cygwin is a POSIX. POSIX is a standard API for Unix-like systems. So it is a POSIX Unix source level. That's very important. Source level API for Windows. I really encourage everyone to use it. So you go to cygwin.com and you install Cygwin on your Windows system if you have Cygwin, if you have Windows. So basically, what is it? This allows you to compile typical Unix programs, for example, coming from uh, Linux, BSD, GNU, whatever. Programs, compile them on Windows. How? By providing a compatibility API, which is implemented through DLL, which emulates Linux Unix system calls on Windows. So basically, your application can invoke any operating system service as supposed to be, let's say, on Linux. It gets into that dynamically linkable library, DLL, and then it is either emulated or translated into native Windows calls, and you have a full illusion that you are running on Linux rather than on Windows. So then the whole world of uh, Linux software can be run on a Windows system. The difference between direct binary compatibility in number one, so this is a binary compatibility, right? And Cygwin is that in order to use Cygwin, you have to recompile your application from sources. When you recompile it from sources, then it runs on top of Cygwin DLL in the Windows environment with some overhead. So a little bit less efficiently than it would be a native application running on Windows, or a native application running on Linux on the same hardware, because there is a slight overhead of this compatibility layer, but it is not really significant. Why it is a good idea? So first of all, because a lot of open source software from GNU Linux BSD had been ported to Cygwin. So if you go to cygwin.com, you install Cygwin, then you get an enormous choice of applications which you can install on your Windows system. And that's typically what I do if, for whatever reason, I'm forced to use Windows. So, for example, if I work for a company and some companies only allow Windows to be used as desktops. So it is a corporate policy, right? So you can't install Linux and run it as you wish on your corporate desktop machine. There is a Windows pre-installed, and I presume there are some corporate features in this Windows. Maybe there are even some elements for, let's say, monitoring what the user is doing. Maybe just recording all internet use, conversations, email sends. Who knows? So then you are forced to use Windows in order to make your working environment at least more or less comfortable for you. Uh, who are used to the POSIX Unix Linux environment, almost the only way is to install Cygwin, and then you get all this uh, conventional, useful, good Linux Linux POSIX stuff available for Windows. Uh, so, for example, in Windows system, there was no, and maybe there is still no official SSH client. You remember we discussed yesterday that SSH is now the standard for remote logins, which uses TLS cryptographic protocol in order to avoid sending plain unsecured passwords. Uh, no one would, in their right mind, would use Telnet on security FTP file transfer protocol nowadays. But for Windows, the standard, well, not the standard, but a kind of standard client for SSH used to be PuTTY. You probably have seen it. It is not part of the Windows operating system. It is a third-party software, which, yes, everyone would install and use, yet it is really a third-party one. If you really want to use SSH in a way convenient for you in Linux or other Unix operating system, then you install Cygwin and use SSH from a Cygwin terminal in a Linux conventional way. And then there is also a system MSys and MinGW. That's a slightly different story, but still we can view it as a compatibility, a kind of compatibility layer. So basically, for each of these operating systems, you have your own compiler suite for, let's say, C, C++ development. Uh, Obviously, for Windows, your compiler suite is whatever Visual Studio, all right? Okay. For Linux, there are currently many open source and not so open source, but maybe still free C and C++ compilers. So for Linux, which C++ compilers have you seen for Linux? Obviously GCC family, all right? Another one is Clang family. But that's not all. So these are two completely open source ones. Then there is an Intel family of compilers. It is not open source, but it may be free if you receive a free license from Intel. And Intel also exists for Windows. Then there is also nowadays a good compiler from NVIDIA, uh, aimed at development of parallel, heavily parallel code, for example, on GPUs under Linux, which probably exists for Windows as well. But the primary one historically used to be Visual Studio for Visual Studio on Windows, and let's say GCC on Linux. And to a very large extent, nowadays GCC is the highest quality C++ compiler around. It is capable of very, very, very heavy code optimizations not seen in any other compilers. Even Clang is lagging behind GCC currently in terms of code optimization. Linux kernel, when we compile Linux kernel, and that's what we will do today, is also compiled using the GCC compiler technology. So obviously, the question is, if it is so good, can you use GCC on Windows as well? Right? Good idea. And the answer is yes. So first of all, GCC does exist within Cygwin. There is a GCC here. But GCC within Cygwin would produce executables which only run on top of this Cygwin DLL. On Windows, yes, but with the help of this Cygwin DLL, which means that there is a minor overhead associated with the Cygwin DLL, and secondly, you can't simply distribute those executables across unprepared Windows operating systems. So they wouldn't run. They would only run on systems where Cygwin DLL is installed. Still, yes, you can do it. And MC's MinGW, MC's was more about just the shell and utilities, but MinGW is a project, now it is MinGW 64, is a project of using GCC to create native Windows executables. In particular, Windows executables which use native Windows API. So this is not about Linux compatibility layer in general. It is more about using GCC compiler to create native Windows executables, where the source level API can be both. If you use MinGW, you can use either the POSIX API to the extent supported by MinGW without the help of Cygwin. So some elements of POSIX API are available. Or you would use native Windows API in that case, or even a mixture of the two. Although it is probably a bad idea, and it is difficult to say whether they are fully compatible and would cooperate. So many ways of how uh, Unix, Linux derived software can nowadays be run on Windows. At least three ways we have identified. Uh, Still, there is one question behind all this. Why do we need Windows in the first place? Only because, I don't know, uh, Microsoft Office suite is high quality and allows you to produce good documents. But even then, historically, There are so many good substitutes. I'm not even talking about OpenOffice, LibreOffice. I'm even talking about Tech, for example, for creating scientific documents, which is, from that point of view, by far superior to any Microsoft Office related stuff. It is a matter of conventions somewhere, sometimes, somehow, compatibility with Windows family is still critically important. Still many corporate environments run Windows, so it is not completely out yet, but I would say to a very large extent superseded by Linux and Mach, and even experienced a very significant code infusion from that. Uh, Even though prior to that, when Windows XP was ruling the world in around 2001, maybe you remember a very popular 20 years ago, a very popular email service, probably as popular as Gmail is now, which was called Hotmail, hotmail.com. That was eventually, it was started in mid 1990s. It was providing the first web driven web interfacing email clients, because before that you had to receive mail into your own local mailboxes and using local mailbox software to operate with it. So it was the first webmail, one of the first webmails, became hugely popular, and then it was eventually acquired by Microsoft. And what do you think? It was an email service which in early 2000s was making probably maybe one third, maybe up to one half, certainly one third of all email traffic in the world. Huge. Do you think Microsoft really ran Hotmail servers on Windows? High load, high performance email servers on Windows? No. Windows kernel was insufficiently performant and insufficiently stable for that. Plus, email, SMTP, email server software, and under Unix, Linux, there are so many of them. And the most widely known are, for example, SendMail, QMail, maybe some others, but I don't remember them anymore. They are very mature, very well developed. There is nothing of that kind actually for Windows. Microsoft Exchange did not have a high performance capability required to run Hotmail at that point. So they completely moved all Hotmail servers, then owned by Microsoft, to which platform? What's your guess? To NetBSD. So even before NetBSD code was directly used in the Windows operating system, even during the Windows XP times, NetBSD was already widely used as a server platform by Microsoft. So it is a great operating system, as well as other BSD derivatives, FreeBSD, OpenBSD, Dragonfly BSD, and so on. So I really hope that, well, based on what we have discussed yesterday and today, you would at least have a look at netbsd.org, obviously freebsd.org, openbsd.org. It is actually a good idea, maybe even to have a hobby of that kind, is to get one computer It may be some, I don't know, your disused notebook or some desktop which you're not using anymore, and install as many different operating systems on it as you like. uh, I wouldn't say install very many Linux distributions, because after all these Linux distributions differ only from the package management point of view, and maybe some configurations, prepackaged software, and so on. Internally, it is the same Linux kernel, and it is the same set of GNU Linux open source, typically open source utilities, right? So the only difference between Linux distributions is how they are packaged and managed and presented and so on. Not a huge difference after all. So installing very many Linux distributions might not be worth just spending time on, but having a look at least NetBSD, FreeBSD uh, is definitely a good idea. Try to, and maybe we'll do it together even in this course, try to install RTEMs, and we'll go through RTEMs to some extent. And of course, we will be using and installing and playing with this SCL4 microkernel, or anything else actually uh, you find interesting. Uh, it might be an interesting idea to compile Darwin. Darwin is also compilable from sources, but it has very restricted hardware compatibility. So basically, Darwin only runs on Apple hardware. It has device drivers uh, for Apple hardware only, uh, or maybe for some hardware which is not native Apple, but directly compatible with Apple. There is a term, Hackintosh. Why? Because the first family, one of the first families of Apple computers was called Apple Macintosh. So Hackintosh are non-native Apple hardware, which is still capable of running Darwin and macOS in general. Have you heard this term? Have you tried ever? Uh,
Not really.
no?
Yes,
Yes? Okay.
yes,
Have you tried to buy any Hackintosh or build any Hackintosh like hardware non-native Apple, but still are trying to run something on top of it?
yes, in 2006.
Oh, okay. And what was it? What kind of hardware? In
It
2000?
was a 2006. It was a specific Dell Optiplex, a specific version of Dell Optiplex, and it was compatible with it.
Oh, so Dell was compatible in that case. Great. Nowadays, I think I did not try it, but I think from all points of view, as long as I saw the spec, that Xiaomi notebooks should be compatible with Mac, should be compatible with Apple. So there may be no point in buying an expensive Apple hardware. You can get a very good Xiaomi substitute. Actually, when I was working for one of software development companies prior to becoming a professor here in Innopolis, I was given a choice of either just the company would provide me with a notebook, either a native Apple or Xiaomi. And you know what? I selected Xiaomi, I did not put, although I didn't put macOS on it, I was using it with, obviously, with Linux, and was absolutely entirely happy with that machine. So, okay, let us now discuss the structure of the Linux operating system. Tell me, please, if you want a 5-minute break, we will do a 5-minute break. How are you? How do you feel?
I'm okay with break.
Okay, let's go 5 minutes. Okay, fine. And then we'll discuss the structure of the Linux operating system. Okay, so we're back online. Let us discuss some very simple things. They look simple, but you know, in computer science, when we study computer science, everything should be finite to the extent that even if we don't know the details of how it works, we at least conceptually understand how the things work. So, okay, suppose that we have developed the following wonderful program in C. Int main, no arguments, return 0, and that's it. So this is our, let's say, test 1C. We compile this program, and from test1.c we get, suppose that we do it in one go, we get test1 executable. Let's say on Linux. Then we run this test1 executable simply by doing dot test1. Typically, there is no path in Linux or in any more or less secure Unix operating system by default to the current directory. So that if you run this executable, you need to specify precisely where it is located, here, in the current directory. Okay, so what exactly would happen in that case? We know that somehow this main program, which we created, would get called and immediately return 0 to the caller. And then if suppose that we are in the shell which is called bash, so after that we examine in the shell the return code by using dollar question mark, and it will return precisely 0, that 0 which our main has returned. Very simple. But the question is, how exactly this works? Okay, anyone who knows the details of Unix Linux operating system can explain or not how this process invocation, this executable invocation would happen, how eventually control would be passed to the main, what happens after main returns 0, and so on. So any exact sequence of events. Not quite?
I have no idea, so...
Let's see. So first of all, when our C program is compiled and an executable is created, there is a special standard format for executables, for both actually executables and shared libraries, which is called ELF in Linux. ELF is executable and linkable format. Actually, you know, what we can do, we can have a look of how it works. Why not? Sorry, I see pluses in your chat response. So plus mean that you can provide an explanation, right? If so, yes, please.
Those pluses were for previous session
Okay.
today.
I will explain myself. So let us go to the terminal. And we'll do exactly that. For the moment, very simple stuff. GCC, specifying the output test1 and compiling test1c. We got test1. Now there's a command in Linux file which tells us what kind of file is it. You see my terminal, right? You can see it.
Yes, it's
Yes.
Yes.
Excuse me, can you see the output in my terminal? I share the screen to show the terminal.
Yes.
I can't see you, I'm afraid.
We can see the terminal.
Oh, it's fine.
Okay.
Okay, fine. So what it says, test1, ELF. ELF is this executable and linkable format, 64-bit, of course. LSB stands for Linux Standard Base, which means that it is compliant to some predefined components which ought to be installed on a Linux or on a normal Linux system. The architecture is, of course, x86-64. Sometimes, and it is actually a better way, x86-64 is spelled with underscore rather than with dash. Both actually notations are used, but more commonly x86_64. Okay, version 1, sys5. Sys5 means basically this ELF format originally appeared in System 5 Descendants, and System 5, as you remember, is one of the descendants of the original AT&T Unix many years ago. Still some ideas from that system may be around. What can we say? We say that there's a command called LDD, which shows us which dynamic libraries this executable uses. Well, what does it use? It uses, first of all, the loader, which is lib64, LD, Linux, and so on. So what does it mean? This executable needs to be loaded into memory and then control passed to this executable in order for it to run. And in order to do that, a loader, which is part of the Linux operating system, is invoked. And interestingly, the kernel does not have the full code which is required for that action internally. Instead, much of this loading operation is done by a user level loader, which is implemented as a shared library. And for that reason, this lib64 LD Linux, which is precisely the loader, is a shared library referenced in each and every, even the most simplistic executable we have created. It is really the most simplistic you could do. about it. libc is a standard C library, which although we do not use directly here, but presumably it is used by the loader or any other shared object. Linux VDSO, virtual direct shared object, is a new edition, so I can't tell you actually for the moment what exactly it does. I think it just implements part of the functionality required by the loader for whatever reason. We may double check that. Okay, we got an executable which refers to a number of shared libraries, and shared libraries are another type of ELF objects which contain some extra functionality, in this case required for this code simply to be loaded and to run. Back now to our whiteboard. Let's see. We are now in the process, which is our shell. The shell is bash. The shell which I am currently using in Linux. Okay. So how this, what happens when we try to invoke our command dot test1, for example. This command dot test1 is first of all simply read into and interpreted by the shell, because we type this command from the console, and bash eventually receives this text dot slash test1 and interprets it as a command. How a reading of user input from a console actually works, this is through the Linux kernel, through the services of the Linux kernel, obviously. Bash doesn't read our keyboard directly. And we'll, in due time, discuss this in general about how input-output works in Unix, Linux, and other operating systems, and eventually coming to SAL for microkernel. So when bash reads this command and understands that it is a path to an executable which needs to be invoked, then how invocation happens? Invocation happens, and this is a standard way. In order to invoke an external command, a new process needs to be created. As we discussed yesterday, you remember, it is about process invocation, process creation. So this is done through a system call which bash performs, which is called fork. Fork is a very, very, very important system call in any Unix system, because that's a way of how a new process is created. And a new process is created in a very simple way. The original process which was running the bash shell is now split into two identical, nearly identical processes. So fork is simply a clone. The current process is cloned. And within the Linux kernel, there is now a new process with a new process ID being recognized and attached to the Linux scheduler. So the scheduler knows that this process needs to run very much as any other existing process in the system. So they would receive CPU time according to whatever priorities, whatever scheduling policy is available for this process. But once again, fork is actually cloning of an existing process. So now fork resulted in two processes, both of them are running bash. Not our test one. No. Test one is not invoked yet. Here bash and here bash. That's a very interesting point. So that's why, by the way, in Linux, although fork is a very, very standard system call, which any Unix kernel performs, but in Linux, fork is just, I would say, a name for the internal implementation of this fork. So internally, the Linux kernel has another Linux-specific system call, which is called clone. So fork is actually implemented via clone. Interestingly, you remember we discussed that yesterday. There are processes, and currently we are creating a new process via fork, and there are threads. And the difference between process and thread is that multiple threads may run in the same address space and would have access to all memory addressable in that address space, whereas a process has its own address space, and entities addressable within that space are not visible from outside by another process, even if they try to access them using the same address. So in Linux, both actually both processes and threads are actually created using this Linux-specific non-standard clone system call. That is a design decision for Linux. Whether it is a good idea or not, we will leave this question out of consideration. Which actually means what I would like to mention in this respect is that threads on Linux are not that much different from processes. We can say threads on Linux are relatively heavyweight. So, for example, if you create, we'll come to that point actually of how to create threads. If you create 1,000 threads, that's probably okay. But if you create 1 million threads within your process in Linux, that's probably a little bit too much. It is a kind of overkill. And that is with current modern Linux operating systems. Previously, for example, in Linux kernels, let's say 2.2, 2.4, even creating more than several hundred threads was already problematic, and for whatever reason would lead to significant performance degradation within those kernels. Not anymore. So current threads in Linux are reasonably efficient, yet we must understand that Linux threads they are to some extent similar to processes because they are being scheduled by the same kernel scheduler. So these are kernel threads, the kernel is fully aware of them. The kernel actually makes no big difference between processes and threads. The only difference is that, as I say, threads may run in the same address space. For a process, a separate address space with a virtual memory map is created. So for the moment, we have executed fork, and we have two copies of bash. The only difference is that the return value of fork is different. So let's say the left branch is the original bash. The original bash, when fork returned, got a process ID of the newly created process. So for example, this was a process ID of, we can actually do this by ourselves. We can do an experiment, but for the sake of the argument, this was the process ID of 1000. Then in Bash itself. Then after it forked, one of them remained 1000, that the original process, and the other one got a process ID of 1001. Then fork has a return value. So we can say some int process ID equals to the result of fork. It's not what we do. It's what is implemented inside Bash. And this process ID, which was returned by fork, in the original Bash, which is 1000, it is the process ID of a newly created process. So now it is here 1001. But the fork is implemented in such a way that the second process, which is created as a clone to the original one, would get a process ID being 0. So what does it mean? It knows that it is a clone by examining the process ID. After that, because both of them continue execution as normal, they would run subsequent commands of what to do after fork. After fork, Bash needs to know where it is, in the original Bash or in a newly created process. So in both cases, Bash would do if PID equals to 0. And here, it would do same if PID, the process ID, equals to 0. So here, the result is false, all right? We're in the original Bash, and therefore the process ID is not 0. So here the result is false. Here the result is true. Process ID is 0 in this case. So false, true. Let's first of all see what it would do if the process ID is indeed 0. So then Bash knows that it is a clone. It is not the original Bash, it is a clone as a result of forking. And that copy of Bash now needs to run our test one, because the whole idea why we do all this story is to run the test one. So now it would execute another system call, which is called exec. Exec, let's say this test one. There are some flags which can be used, but for the moment, it is sufficient to do this exec. So what does it mean? Exec completely replaces the current running image of the process. Before that, it was running the code of Bash. Now exec completely replaces that executable code, fully completely replaces it by the code of this test1 executable. So from that point of view, it is test1 rather than Bash gets executed. Here, it would be same, of course, code in Bash exec, for example, in this case, our process, but the condition is false, and therefore this exec does not occur. So what it would do instead, okay, it does not, Bash does not replace itself, the original version of Bash does not replace itself by a copy, by test1. So Bash remains Bash, in this case. So what do you think bash would do? Else? So, okay, it is false. Here, of course, else as well. Only different paths are taken. So, okay, it is not replacing itself with test one. So what does bash do? Any ideas, please, your ideas.
Just creates a copy of itself and that's it.
You see, it has already created a copy of itself here when fork was done. And that copy then got replaced as a result of exec by the newly created executable. Here is the original bash. The original bash simply waits until this program terminates. So it executes yet another system call, which is wait.
Sorry.
Yeah.
This fork, it makes two processes, or this works inside one process?
Good point. A fork creates plus one process.
So how this wait works? I mean, if they are two separate processes, they don't have any executable memory, and therefore one process don't know what happens with the other one. Am I
They
wrong?
do. Let's see in detail. So first of all, fork doesn't create two processes. Fork creates one process. One additional. So I would say the left hand branch is the original bash. So that's the original bash. Okay. But at forking point, we created another copy of bash at that point. Okay. So there was one bash, that bash continues to exist. Now after fork, a new copy of bash is created. And by the
Sorry.
way, yes?
And by process, you mean that they are allocated some memory that they will
Yes,
use?
yes. So
But this
fork,
memory are separate. So
absolutely right. You are absolutely right. So what fork does, it allocates a completely new address space for the new process, but it copies fully the content of the original process into the new address space. So indeed, fork is a clone. Think of it as a clone. So it created a completely new memory range, newly addressable space in a completely separate segment of memory, completely unrelated to the original one, and copied completely entirely the content of the original bash into the new process. And that's why for a second, instantaneously, both of them continue to execute the same bash code, because the second process is just an almost exact copy of the original one. I would say almost exact. What is the difference? Between the original one and the new one? The difference
ID?
is, yes, the process ID, the PID, is different. More precisely, the return value of fork is different. So the return value of fork is stored in the PID variable. Like here, int PID equals to fork. So the return value of fork, which gets stored into PID, is different. In the original bash, it is equal to the process ID of a newly created process. Whereas in the clone, the return value is 0. It is just a convention. A possible alternative would be to, for example, in the cloned process, to return the process ID of the parent. but it is not necessary because it could have obtained this parent process ID another way. So there is little use of that. So this scheme works. In the parent is bash. The return value is the process ID of the child. In the child, the return value is 0. And therefore, both versions of bash continue execution, and then they execute the same if statement, if PID equals to 0. Only the result is different.
I'm sorry.
Yeah?
And if the child process has ID of 0, there can be multiple
No, sorry.
No?
No, the child process doesn't have an ID of 0. The child process has an ID of 1001.
And the
That-
return value.
But the return value is 0.
Okay. Okay, thank
If
you.
the child process wants to know its own PID, it can do it very easily by executing the system call getPID. So it will know its own PID. If it needs to know it eventually. That's the whole point. It got an absolutely real and valid new process ID 1001, but the fork returned 0. It returned 0 in order to just be able to very easily distinguish where we are, in the parent or in the child. Okay?
No.
And okay, please, you know,
Yes.
that's a very important concept. So don't be shy. Please answer. Please ask any questions if anything is not clear.
So if the child returns anything besides return 0, maybe return 1, then what happens?
The fork will not return 1 for a child. If it is a child, fork will always return 0. Fork may return -1 if for whatever reason creation of a child failed. That is also possible. Return values for Unix system calls which are negative, they always indicate an error. Why could it be? It could be, for example, that the limit on the maximum number of processes you can create is reached. It is not always possible to, for example, for an unprivileged process to clone itself 1 million times. There are some limits. Actually, in Bash, I'm switching to our console. Once again, you can see these limits very easily. There is a command in Bash which is called ulimit. Ulimit, and to see all, we say -a. -a is all. So we see these limits. So for example, where is, if there is no such a limit, then there is no limit. Max user process. You see, max user process. So this user, myself, at the moment, so I am not a root, I am not a privileged user. I am a user called Leonid at the moment, as you can see, all right? With user ID 1000. I can only create, for whatever reason, 62,819 processes. I can't create 1 million processes. So if I do fork, then eventually I run out of available process for me. And at that point, a clone would not be created, and my fork will get -1. I can't open too many files at the same time. I am only allowed to open 1024 files, and so on. POSIX message queues is a method for inter-process communication. Also, I can't create too many messages. But now, if I execute the sudo command and I become a root, so now you see I'm a root. And under root, I do same ulimit minus a. Then you see that, interestingly, nothing changed, and I have same set of limits for the root. But I can now explicitly lift this limit. So for example, I can, if I want to, for example, be able to create an unlimited number of processes, I would say u limit minus u, here is a hint, unlimited. And now I have an unlimited number of user processes I can create. It's because I'm a root. But if I get back from the root to being just Leonid, and I do a similar command, u limit minus u unlimited, it says no, you can't. You can't allow yourself to make an unlimited number of processes, of your child process. For root, you can do it. For an ordinary user, you can't. So getting back to our picture, a fork created a clone of bash, with the only difference is that the return value of fork is the child PID in the parent and 0 in the other case. Okay? So please, just at this point, is it okay or not quite?
For me, it's okay.
Okay, great. Now, because for the moment, apart from this value of speed, they are still identical. So the second process is now a clone of bash. They run the same code as in bash. And what is this code in bash? In bash, it is an if, a conditional. If PID equals to 0. Here and here, it is exactly the same code, actually, on the left and on the right. Only the outcome is different. So I put this code. You see, it is absolutely identical. If PID equals to 0, then exec, else wait for the PID. But the results are completely different. In the child, where the returned PID is indeed 0, the conditional is true, and therefore, what next happens is exec. Exec results in a complete replacement of the current code by the code of our test one. So that's all. From this point on, our test one starts executing. How, we'll see. So that's all. This code, which was originally in bash, is no longer existent here in the child. It got completely replaced by our test one code as a result of making this system call called exec. Exec, and there are some variants of exec, exec and friends. Okay? But here, here is another situation. The conditional is false, therefore exec doesn't happen, and then bash continues, and bash goes into the else branch, and it simply waits for this process ID, for the PID. What does it mean, waits? It means that bash is suspended and doesn't do anything until our test one is completed. So it waits for this test 1 to be completed. Because test 1 does nothing, as you can guess, it gets completed very soon. All right? Because test 1 only invokes main, and main immediately returns 0. To whom?
Sorry. Yes, if they have like a different memory allocation, they have to share some memory to know to the left one knows that the right one ended, right?
Not exactly. Not
Okay.
exactly, because wait is a kernel call again. So in this case, bash by itself doesn't need to know anything. The kernel does, because the kernel has access to all memory. And therefore, the kernel obviously does know when the child terminates. Bash itself does not. Bash has absolutely no access to the child and has absolutely no idea. So what exactly wait does, the wait is a kernel call. It's not like, let's say, a semaphore, which is implemented within bash. Wait is a call to the kernel. When this call is made, the kernel suspends further execution of bash until really this specified PID becomes completed. So basically, bash asks the kernel, suspend me. I would progress no longer until this process ID, which I'm interested in, this created PID, becomes done. And indeed, the kernel obviously knows that, because the kernel scheduler is aware of all process IDs and the states of all processes. So it knows that at this point, for example, it was not done yet, but in the next timer tick, which occurred 1 millisecond later, suppose that, then our test 1 already terminates. So then the kernel, having seen that it has terminated, it basically returns from wait, allows bash to return from wait. And moreover, what it returns from wait is the return code. So let's say RC, and here RC, and before that we would say int RC equals to 0 for the same of the argument, for the sake of the argument. There should be identical code on both sides. Int RC equals to 0. So now RC becomes the return code of our process, this PID. What is this return code? That's basically, not exactly, but for the moment, that's basically what a return did in main. You remember, in our main, there was a return 0. So eventually, how exactly we'll need to see in detail. But eventually, this return value will get into the kernel, and the kernel will return it to the caller of wait. And after that, bash continues its normal way. It will wait for more commands from the command, from the terminal, from the console, and possibly run other commands. So bash is just, well, here, in the simplest way, is an infinite loop of get a command from the keyboard, run it through a fork and exec, and wait for completion, and do it again and again, over and over. Please look at this. Any questions? If not, it is 2 p.m. exactly. So we make a break and we continue in 10 minutes. Okay?
Sure, great.
At 2:10, there will be the next lecture. Thank you. Okay, we are back. Everyone is okay?
Yes.
Okay.
Yes.
Let's continue. Wonderful. So, as you can see, there are three most important system calls we have seen here: fork, exec, and wait. Fork is actually quite a complex one because it has to create a completely new memory area and copy the current process into that memory area. Plus, do a lot of housekeeping because this new process will have a new process ID. Inside the operating system, there is a process control block, which contains all information about the currently runnable process. This process control block is attached to the scheduler of the operating system, which then, by examining the process control blocks, allow some process to run, or maybe other way around, suspend some process. Like, for example, here our bash was suspended. It suspended itself voluntarily by executing wait because it really wanted to wait until the child process completes. Exec is also a relatively complex system call. So what exec does? Let's see what exec could do. First of all, exec needs to completely remove all content of memory currently occupied by this newly created process. So actually, as you can see, the combination of fork and exec is not very efficient. When fork is done, then first of all, bash content is completely copied into the new memory area. Only after just one if, it is completely erased and replaced by new content. It's not a very good idea. What do you think? It would be much better to have some kind of maybe direct fork and exec combination, which would do these two things at once. But the traditional standard way of doing things in Unix systems is really to do it just by this combination fork plus exec. It may very well be that in modern Linux kernel, it is somehow optimized. So it may be that, for example, the fork would not even copy all data completely, but only maybe some part which is some part of code which needs to be run and to make a decision that we're in exec subsequently. So some kind of optimization is possible. It might be an interesting idea to have a look at Linux kernel sources to see whether there are special optimizations for the fork and exec sequences, because it really looks wasteful. Copy bash into the newly created address space first, and then erase it completely and replace it by the content of text one, of test one. Anyway, when exec system call runs, it runs within the kernel, so that's what the kernel does. What do you think the kernel would do? So how exec is actually performed? First of all, the kernel needs to find the file referenced in exec. Which is exec argument. Okay. Then, what the kernel would do? not all files are executable. If this is your Microsoft doc file, then it is not possible to execute it. So the kernel checks the format of this file.
What do you mean by format? The last.
I mean that each file has in the initial bytes of this file some kind of signature which represent the file type. Exactly when I will get back to our terminal. If you remember, we did it already. We did the command which was called file, and then it was, I have quite a lot here. So for example, our file test1, it says, yes, it is ALF 64-bit executable. There is a binary signature. Oh, sorry, test1. If we view this file in a binary format, you see in the very first bytes, there is a signature ELF, indicating that it is an ELF type executable. Or maybe, do I have BVI available here? No, not BVI, but VI itself. You see? A signature containing ELF. So the kernel also examines this signature. It doesn't check the file completely. Then it will start reading the file. If it has a wrong format at some point, then it will be detected. So currently there are two types of files which can be executed as executables. So one of them is indeed ELF. Can you see the whiteboard now? Or the terminal? The whiteboard.
Terminal.
Okay, just a second. I will switch back. Yes, that's what you say. Each file inside Linux has a header that defines the type. Indeed, that's the signature I was referring to. Indeed. So going back to our whiteboard. Two types of files can be executed. Either ELF executables. These are really binary executable files. In other operating systems, the executable types could be different. So for example, Windows .exe files, they have another executable format, which is not ELF. Or files starting with text files, actually. Text files starting with hash exclamation mark. These are various scripts. So in order to, and then there would be a path to the executable which actually runs this script. No doubt you have created scripts on the Linux, right? For example, bash scripts. So what is the first line you do in a bash script? Let's see. You see, hash exclamation mark and then pass to the executable which will run this script. Okay. Then the kernel actually looks for this executable, invokes this executable, and gets this executable, read the rest of the file from the standard input. And then the executable starts running the corresponding script. So that's how it works. And it is really the decision which is up to the kernel, which executable files to allow. When we go through the Linux kernel, we will see that these functionalities, for example, allow running ELF and hash exclamation mark type files, is a very common configuration. Although, if you really want, you can recompile your Linux kernel so that, for example, scripts would not be runnable at all. So you can deconfigure this. If for whatever reason you don't want to run scripts directly, in that case, you would have to run the executable first, I mean, for example, another bash or whatever, followed by, in the command line, followed by the script name. This will also work. But in order to simplify invocation of executables, this is done as a shorthand, as a shortcut. ELF executables, and if you execute a script, then also an ELF executable will be invoked, only it is the interpreter for that script. So in any case, the kernel must load some ELF executable into memory. ELF executables have a relatively complex structure, and typically it would contain a so-called text section. What is a text section? Text section is simply binary code, machine command. But for historical reasons, it is called text.
Oh, we see your terminal.
You see the terminal rather than, sorry, switching between the two. Okay. So, we're here. ELF executable would contain a text section, which really contains the machine code. It would contain some data section, BSS section, both actually data and BSS contain data. Only data by themselves are uninitialized and BSS are initialized, if I remember correctly. And these sections could be optimized. So for example, if you create some static uninitialized array of very big size, then it doesn't need to be created directly in your ELF executable. So it wouldn't make your ELF executable huge. It will only be recorded in the executable that, for example, 1 gigabyte long array uninitialized needs to be put into your data section, and actually the memory for that would be allocated when the file is loaded into the memory. There is absolutely no need to keep those long uninitialized data in ELF files when the program is compiled. So and so on. Actually, the structure of ELF is an interesting and relatively complex one. And especially what is important is that when a file is loaded, as we could see, This is done with the help of LD loader, which is an application level program in Linux, but it is also part of the operating system. It is not part of the kernel, but it is a part of the operating system, because without that, none of your code would become loadable anymore. So a very easy way of how you can, for example, damage your Linux operating system beyond any usability is simply to delete or overwrite this LDSO loader. And then nothing actually will help you. You wouldn't be able to execute any command after that. And by the way, do you have any idea what to do if that happened?
Restart kernel.
Sorry?
Restart kernel maybe, or something like that.
No, you restart the kernel and then still you wouldn't be able to execute any single command because your loader is damaged. This loader LDSO is a shared library or a kind of DLL if we use Windows terminology, which gets invoked during the process when the kernel loads a new executable into memory. So if this DLL is damaged, then nothing will help you. Getting back to the terminal, once again, LDD our test1. You see this, for example, lib64 ld linux whatever. It is just a file. It is a shared library in our file system. Okay, it is a symlink to LD232. Okay, so what is LD232? It is a shared library of about 264 kilobytes, something like that. So if by any means I damage this shared library, I would not be able to run any single command on my Linux system. If I reboot the kernel, it wouldn't help because the kernel, when performing the exec system call, does only part of work, and the rest is done by this shared library. So the kernel would still be referring to this shared library, not because it knows about it, but because the path to this shared library is built into the executable.
Can we somehow restore these files, but from any disk or USB or something like that?
Yes.
Copy it.
So basically what we'll have to do is to boot the system from a rescue media, which would have its own root file system. It would have its own, in particular, lib64 LDSO loader. Mount your original file system as an auxiliary file system, not the main one. Mount it under a certain path. Copy a correct loader over from the rescue disk into that location, and after that reboot your system. By the way, in this connection, I will tell you a story, simply because it happened to me nearly this, actually, nearly this. Once, and it took me a day to investigate, and that's terrible. That was terrible. I probably received a lot of gray hair as a result. So the situation was, as I understood subsequently, you can't imagine, but it was the case. You know what Adobe Flash is? Flash player.
Yes.
Flash player. Okay. It is not the native Linux software. They did provide Linux compatibility for a while. I think now they uh, do not even provide it, so it is not available for Linux anymore. But Linux has its own Flash player format, which is Flash format player, which is called Gnesh. And in any way, I think with the advent of HTML5, Flash is not important, is not as important nowadays as it used to be. So now a combination of HTML5 and JavaScript is perfectly sufficient, and Adobe Flash technology is not required anymore. But that was about 4 years ago, and at that time Flash was still needed, and I installed a Flash player on my Linux system. I did not even realize that it was Flash installed, but when I rebooted my system, not immediately, so I installed Flash, then I was continuing to use it maybe for half a day, maybe for a day, I don't remember, and then I eventually rebooted my system, and my Linux system plainly refused to boot. So I could see that the kernel was booting up. So the startup messages in the Linux kernel did occur on the screen. And then at the end, it was unable even to launch the first process, the init, process number 1, as we have seen it. My God, why? Our init, so let's see, it is sbin init, which is actually libsystemd nowadays. Okay, and this systemd, it is also an ELF executable. And you see this ELF executable, it refers to a lot of shared libraries. You see the output of my LDD command, right? It uses a lot of shared libraries. In particular, yes, under this lib64, it had this LD Linux and so on and so on. So it still needs a loader, simply because it is just a normal ELF type executable. My God. If we look at the top level file structure of a Linux system, then you see that there are, can you see it in color? So blue ones are directories, whereas these cyan ones are symbolic links. So basically, although our LD Linux is located under lib64, LD Linux, and so on, but in fact, lib64 and lib itself are just symbolic links to userlib and userlib64. Which are two separate directories, actually. It depends on, by the way, this depends on your Linux distribution. Sometimes they are separate, lib and lib64. Sometimes lib64 is, and that was actually on my system on Arch Linux, actually lib was just a symbolic link pointing to lib64. So everything was in lib64. Here in Fedora, they're different. What the installer, so in fact, at that time, it was just one directory. all this /lib/lib64 /user_lib/user_lib64, when in fact symbolic links to just one directory, which was user lib64. The installer of Adobe Flash Player, damn it, disregarded the existing symbolic link, deleted the symbolic link, and created a separate directory /lib, into which it puts its own shared library and nothing else. As a result, all passes to the system loader required by absolutely all applications became broken. Can you imagine that? And not a single executable could run on the system. It was not even possible to complete the boot up process of the system, because in order to do that, you had to run this ccnit, and ccnit was not running. It was looking for the loader, again under the corresponding path, which was no longer valid, because the installer of Adobe Flash Player removed a symlink and created a separate unrelated directory under the same name. How? You know, it took me a day to figure out what was wrong. So if you, that's a hint for you, if you experience unexpected and strange failures of your booting up process at the point when your ccnit is to be launched, then it may very well happen due to a reason that something wrong occurred with passes to your critical shared libraries, and the most critical shared library in this dynamic loader. The dynamic loader gets executed when the kernel loads your code into the shared memory by executing the exec system call. Nice, isn't it? Okay. So then, suppose that eventually our ELF executable, which is our test1, got loaded into memory. So now in memory, we have this, first of all, we have this process with the process ID equal to 1001. Okay, I'm switching back to, the whiteboard. Yes, Adobe Flash is no longer maintained. Rightly so. I would rather live without Adobe Flash than to experience an incident like that. I nearly got a heart attack. And going back to our whiteboard. So the process ID is 1001, and now it is really this text data, BSS, whatever, segments living in memory of our test1 executable. Okay, so in order for this executable to run, notionally, from our C programming point of view, the first entity to run is our main program, right? Main is the first entry point, correct? The answer is not exactly. The main is not really the first one. Okay, with C, this may look a little bit more difficult to answer, but I presume of you there are some familiar with C++ programming, right?
Yes.
Can you tell me, please, Dan, which code in a C++ program may run before main and will run before main?
I'm not sure, but I've heard of CRT0 or CRT1 that can be run before.
You are right. You are right. But CRT0, CRT1 is not the code available to us. All right. So if we in our program would like to create some code which runs before main, what would we do?
Maybe include something.
Oh,
Uh,
no.
Inputs.
No, not necessarily. Include is only a textual include, which typically provides for the code which is included does not run. It is only typically declarations for the compiler, which allows us to, for example, which provides context, which allows us to call certain library functions, because includes typically contain declarations for those library functions. So the compiler knows how to generate the code. No. So included code, although it is textually included before main, it is not run. It's typically declarations only. But what runs before main? Constructors of global objects run before main. Let's check this. So now instead of test 1, we do test 2, and it is a C++ program now, not C. Test 2 CPP. Okay? Again, we do not even include anything.
We can see your terminal, by the way.
You can see the terminal. Sorry, I pressed some wrong button. Just a second. Okay. The terminal. Here we are. Okay. So we are now creating a C++ program, and to make it visible, okay, I will do some include. Include IOStream. Then I do a very simple class. In this class, there is nothing, but there is a constructor. There is a default constructor, which says that it is a class 1 constructor. Why not? Such a class. Okay. And now there is an int main. In this case, class 1 is only declared, and there is no global object of class 1, and therefore the constructor would not be invoked. But let us create a global object. So I would say class 1, object 1. And now object 1 is a global object, and constructor of this global object needs to be, and here we will do we say y in main, all right? Run it. As you see, class 1 constructor runs first and main only second. And then we're coming to the point which you precisely identified, that there is some standard code which runs before. Yes, it comes into CRT0 startup file which gets linked with your executable, but for our purpose, it is sufficient to realize that each ELF object has some standard entry point. And this entry point is not main. This entry point runs some initialization code. Of course, this standard entry point is a part of the text segment. It runs some initialization, which may be very complex actually, because you see here, this initialization code for C++ program, it needs to somehow find all global objects whose constructors need to run and then execute those constructors in a particular order. This is done actually by creating extra sections, for example, sections init and fini in our ELF file, and the compiler, it doesn't need to be C++ compiler, it may be a C compiler as well, but for C, we would need to do it manually, artificially, whereas in C++ it is very easy. Just create a global object and you will make sure its constructor runs first before the main. How to put initialization code into C so that it would run before main. It is just more involved and would require manual tweaking, which I'm not discussing now. But in both cases, there is an init section, and the startup code reads this init section in order to see which code needs to run first, and only then, after all this done, eventually at some point, your main runs. Okay? It runs your main. Main results in a return. So in that case, we have return 0, right? Return 0 from main. When we return, to where do we return?
To the parent process we return?
Sorry, to where?
Parent process?
Not yet. No, definitely not to the parent process. The parent process is completely detached from our child process. It only waits for completion. So yes, when we eventually return, the parent process will get our return code and it will be released from wait. But it doesn't mean that we exactly return to the parent process. When we eventually return, then simply the parent process resumes execution because it will be notified by the operating system that the wait is over. And if it may very well be that the parent process does not wait for the child, obviously, you know, parent waiting for the child is a common paradigm, but it is not necessarily the case. It may very well be that it's not a good practice, but it may happen that the parent simply doesn't wait for the child. The parent continues execution its own way, because it is just a completely standalone process running in the operating system. Here, when main returns, then it returns first of all into the startup code. And the startup code then terminates the whole process by making yet another kernel call, which is either exit or there is a kernel call exit with underscore. And then you can specify, for example, your return code, 0, 0 in any case. So basically, return when RC return code is returned from main, that return code is then used by the startup code as an argument to exit, and it is exit which returns to the operating system. When exit is performed, then the operating system scheduler destroys the whole process because the process has exited. The process ID PID becomes available. So for example, if then a new fork occurs, then this process ID may be reused. No one can guarantee that the process ID will be unique for any amount of time. So for that reason, actually, referring to processes globally by process ID, if you don't know for sure when the process could have terminated or not, is a bad idea. If, for example, the parent needs to communicate with the child somehow, and there are mechanisms which are called IPC, inter-process communication, in Unix Linux. This is a very important part of any operating system. Then the parent needs to know actually whether the child is still active or it has terminated. The fact that there might be a process ID with the same number, it doesn't really mean that it is still your own child. It may be that your child has terminated and another process was created with the same process ID. And that's the reason why the parent should normally do wait, because in that case, it would know for sure whether the child exists or not.
Excuse me, I had a question. What is the task of PID log file?
Yes, this is precisely when you created a process to store somewhere in the file system information about the process ID of that process. Very often, many components, many other processes in your operating system would be interested in precisely that a certain important process in the operating system is running and what is its process ID. You see, in the scheme which we discussed so far, only the parent knows the process ID of the child, right? The parent, when it executes fork, it does know the process ID of the child. But other processes unrelated to this parent, they do not know process IDs of other processes. But suppose that for whatever reason, they do need to know. So for example, I have some important daemon or continuously running process in my operating system, which provides some useful services. I may communicate with this process using whatever IPC mechanism, this inter-process communication. And for that reason, I need to know the process ID. How can I know the process ID? In order to know the process ID, we simply agree on some standard well-known location, which is really under, for example, a run directory, a certain .pid file. And then by looking up that .pid file, even unrelated processes, which are not parents or children, they can know the process ID, which may be useful. Another reason, another use for the same technology is to prevent same process to launch twice. Suppose that you only want one copy of this process to exist at any time. For example, your process is a graphical display manager. So obviously, if you launch two instances of them, they would conflict with each other. When the first one starts, it creates this lock .pid or pid.lock or whatever file. The only important thing is that it is a kind of standard name which this process and possibly other applications know about. If it encounters that this file exists in the file system upon startup, it does not really mean that the corresponding process exists. because it may very well be that the process has crashed. For example, there was a crash in the operating system. So what it would then do, it would read the process ID from that file, trying to detect whether the corresponding process ID is running. And if it is indeed running, then although it may not be the same process, the same executable, it may have been reused. But to be on a conservative side, our new invocation of, let's say, the display manager would refuse to run if this lockpid exists and the process ID extracted from that file really appears to be running, no matter whether it is just our process or another one. So it would produce an error message that refusing to start because the corresponding process is probably already running. If it is a false alarm, then you would have to either remove this file or kill that process which was invoked wrongly. Well, one way or another, investigate this situation and make sure that your process will start. So for that reason, so to make a short answer to your question, to let other processes know if they need about the process ID of this process. Okay? So really a return to the operating system is not when main executes return. It's when the startup code executes exit or underscore exit. The difference between exit and underscore exit is subtle. Suppose that the current process has some file descriptors open. So for example, it was doing some file or socket IO. And you know that the low-level mechanism for file and socket IO is in Linux, Unix, POSIX API is via file descriptors, FDs. If you wrote some data into a file descriptor, then it may very well be that this data were not yet flushed, for example, on the disk. And if you terminate your application abruptly, then the data may be lost. They wouldn't be saved. Exit without underscore is still trying at least to correctly close the currently open file descriptors and do some other gentle termination stuff. In particular, as far as I remember, it would still try to call the code in the fini section. This needs to be checked, but definitely closing the file descriptors. Yes. Exit with underscore is absolutely unconditional exit, which does not try to be nice, graceful with files or any other code at all, immediately returns control to the operating system. And at that point, which might be a good idea, because if you suspect that you may experience some crash during your finalization code, for example, then it is a better idea not to execute it and to return to the operating system immediately to save you from one more trouble. That's what we do. And then the operating system completely removes the corresponding process, cleans up its memory, and notifies the parent, if it is waiting for this child to complete, about the completion, and eventually returning this return code to the parent as the value returned by wait. Okay? And we can, instead of doing return, we can use exit and underscore exit in our code directly. Why this could be useful? Because return is only a return from main. If you have any subprograms, any functions, any methods, then obviously a return from them would only be a return to the caller rather than returning from the entire application. So in that case, if you need for whatever reason to terminate immediately, you would use exit, or even if very, 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 very immediately, underscore exit. That's how it works. Short break and then we continue. Okay.
Okay.
Okay, let's get back to our stuff. Now we will examine a very simple operation, which is, you know what, which is a keyboard read from the operating system's point of view.
I'm sorry, I still didn't understand why do we need parent in the first place?
Why do we need parent? Okay, good point. Let's discuss, suppose that we don't have a parent. How would the child be created? Let's discuss alternative variables. Okay, there is no parent. where would this child come from?
From the bash and then
But
execute.
bash is a parent. Bash is precisely the parent in this case.
I mean, okay, no child at all.
No child at all. So bash performs all operations by itself, right?
Yes, it simply just calls execute and that's
It
all.
might be. Yes, it might be, but that was a deliberate design decision which was taken 50 years ago when Linux was in its infancy, that we really create new processes. So in general, it might be, you are right, in this scheme, it would be perfectly possible to implement the following scheme. So we don't have a fork. We somehow load the new code into the current process, execute it, and then when the code returns, continue with the current process, which is bash, right? For example, that was your proposal, correct?
Yes.
You see, there are drawbacks with this. So first of all, in this case, the code which you load would be executed in the address space of the current process. If that code which is to be loaded and executed is erroneous for some reason, it may damage not only itself, but also damage the data structures of your current process. So for example, you're developing a program, you made a pointer arithmetic error in your program, using a wrong pointer, you zeroed out a memory which actually belongs in that case to bash, because your code executes in the same address space as bash. And that's a very bad idea, because then your environment would crash and you would have to either restart bash or restart the whole operating system. So it is quite inconvenient. So the whole idea is precisely that. When you execute a third party, let's say, command or a third party program, then to be able to be able to execute it in a completely separate process environment, in particular in a completely separate memory map, which is unrelated to your parent, and therefore at least you would be able to save the parent from accidental damage. That's one advantage of doing it via fork. Another advantage is that fork also allows you to execute the code in a second process concurrently. You remember that in Linux it is possible to start process with the ampersand at the end of the command line, which means that bash will not wait at least immediately for completion of this process. So the work cycle which I presented is just, I would say, the simplest one. And this simplest one, it means that really the parent waits for the child to complete. The parent may not wait for the child to complete, or at least not wait immediately. You can start another process in the background. That's what it means to start in the background. It means do a fork, do an exec, but do not wait immediately for the child to complete. In the meantime, the parent, for example, bash, can receive other commands, do some other work, and only maybe at some later point wait for the child when it would expect that the time was already high for the child to complete, then wait for it, or maybe not wait for it at all, although not waiting at all is considered to be a bad practice, because a child not waited for at all is called zombie. It is a zombie process. Again, there is nothing wrong with that, but it is recommended that you would still sooner or later, maybe not immediately, but sooner or later, execute a wait. So basically, this is for two reasons. to protect the parent from accidental damage and to allow concurrent execution of parent and child. In particular, parent and child could communicate with each other, exchange messages, do something else through this inter-process communication mechanism, and conceptually run concurrently on a true parallel hardware, run in parallel, as we discussed last time. So these are two main motivations behind this idea. What is a disadvantage of this idea is slightly inefficient invocation. As I said, fork followed by exec is a little bit inefficient, but typically we do not know that very often. If we really need lightweight concurrency, then we would create threads rather than process. And upon creating a thread, you do not do exec. Because if you create a thread and you do exec, then the new executable would completely replace the current one, not the current thread, but the whole process, and kill all created threads. So with threads, it is a more lightweight technique, which is probably more close to what you are thinking about. So first of all, then there is no memory division between them, and there is a lighter weight invocation mechanism. And yet, you would be able to create a thread and then run the original part of your process and the newly created thread concurrently, or maybe in parallel. Okay? If anything else is unclear, please feel free to ask.
Can you just briefly say about the data and BSS?
Okay, yes, I mentioned that. Let us, you know what? Why should I say? I would show this. Let us do precisely what you're asking about. Going back to our favorite development instrument, which is the terminal. Okay, what should we do? Returning to our test one. That's our test one, all right? Very, very simple one. As you remember, when I compiled test one, I immediately produced the executable. But in fact, it is not like that. First, the object file of this test one is produced, and then it is linked with maybe some external libraries, and the executable is produced. So these are two different processes. So to do it in two stages rather than in one stage, first of all, we just compile with the flag -c our test1 source. As a result, we got a file which is called test1.o. This is not yet an executable. This is an object file. So let's see what this object file, how this object file is composed. So what it is composed of. We have a very useful command, which is called nm in Linux, which shows us the layout of a test1 object. As you see here, there is not much. It only has one entry with a relative address of 0. It doesn't mean that it is going to be 0 when it is invoked, obviously, because currently we're only talking about this particular object file. T precisely means it is in the text segment, and it is main. So not much here. But let us modify our test1 and see what will happen. So apart from this, we will create two objects. So first of all, we will create some int n, which is immediately initialized to 10. And we will create int m, which is not initialized. And then we'll make our main little bit more interesting. We'll say, first of all, m equals to n, and then we return m. Compile it once again. What would NM show this time? Aha. Can you see it? B is BSS, D is data. We still have our main, T main, but now we have M under BSS and N under D. Remember this. M BSS, N data. So let's have a look again. N data. From this you can see clearly that initialized global data come into data, uninitialized come into BSS. Okay, now a little bit more about this. These are just two integers, and you see that the object file which we created is still pretty small. Okay, it is only 1440 bytes. If we compile our program with the maximum optimization with -03, it may even become smaller, although I don't think it will be much smaller, because this one doesn't do much. No, it actually became larger, as you can see in this particular case. But applying NM to it once again, we again see that we have a BSS main, BSS text and data, and comes into data. Okay. By the way, if in C or C++ we apply the static keyword outside of any function, then you will see the result. They are not visible anymore. So you see, in this case, they are not exported, and other programs will not be able to see it. Those BSS, so which why actually not? Because I think they were optimized out. If I compile it without optimization, then they're still available. But you see, these are now B lowercase and D lowercase compared to B capital and D capital previously. What does it mean? This means that they still appear in the corresponding segments, but external modulus, other object files which are eventually going to be linked with this one, can't see them because they are currently local symbols per file, file specific, rather than global ones. This is just for illustration purposes, don't worry much about this. So just to, let's not play with the static, you will encounter it later on when you need. For the moment, just we just come to this. So we have this initialized and uninitialized data. D is data is initialized, BSS is not. Now suppose that instead of this just M, I will create a huge array of integers of, let's say, 1 million integers. What do you think? This 1 million, the space for 1 million integers, would it come into our object file? Will it create our, okay, I can't do this assignment anymore, so I do return n in that case. Do you think that we need to store this 1 million integers 4 megabytes in the object file? These are uninitialized data. We just say that we want this data to be reserved. So hopefully not. Hopefully this M would not come into our object file. When it is loaded into memory, then yes, M would be created, but we don't need to create it right now. So let's see. We still have this BTD and D, and what about the size of our object file? It is still small, so there are no megabytes here. Uninitialized data do not need to be present in the object file. It is only as an indication for the loader, for the operating system loader, to create the corresponding BSS segment and the M array in it when it is loaded into memory. For the moment, we don't need to keep it into the file, in the file. If we do it for N, then the situation might be different. So suppose that I'm trying to initialize the array. I don't think it will work in C. It may work only in C++, but let's try. So for N, I create a similar one and try to initialize it to 0, although again, this construct, this type of initialization might not be available in C and only available in C++. Let's see. Oh, sorry. We can't return N anymore. I return 0. Okay, it did compile. So what about our NM? Again, but now you see that both of them came into BSS. N is BSS also. It's not in data anymore. It used to be in data, but now it is in BSS. So the compiler performed, and we see the size of our object file is small again. So look at this. That's a very clever trick. N is notionally initialized, but the compiler still put it into the BSS segment in order not to create a very large object file. Instead, it created a code which would dynamically, upon startup, write zeros into the corresponding array. So the clever compiler put both N and M into BSS rather than putting N into data and creating a huge zero initialized data segment as a result. Good, isn't it? So that,
Yes,
yeah.
Also the address of the N has changed.
You say the order has changed.
The address.
The address of it. Yes.
If you
Yes,
here NM.
Yes, it did change. And this 3D 0900 precisely tells, very good observation, thank you for pointing it out. It really tells us where it is going to be in memory when loaded into memory. But it doesn't mean that it needs to be with the corresponding intermediate zeros in the object file. Yes, so it comes at this address. I'm absolutely sure that this address is precisely the offset of 4 million bytes. We can easily see it. So instead of 1 million, okay, so 4 million we say, okay, therefore I just, you can recalculate it. So I'm absolutely sure it will be the length of that array. Which tells the loader that when deployed in memory, yes, put N of that length, and after that put M. Because N is now a long one. but the object file by itself is pretty small. Very good, very well spotted. Okay.
Okay.
So now let us do another very important, we'll use another very important tool. Okay, that's what we did. We produced an object file. Now from this object file, I would like to produce an executable. I don't need to compile this source from the beginning. I do already have an object file. So I have GCC now -o, not -c, but -o test1 to produce an executable. And it is test1.o, which is the object file already compiled from .c. And I now have this test1 executable, which is probably a bit larger. How big is test2, by the way? No, they're about the same size. Test1 and test2, and if I run test1, I still get this 0 as a return code. So now let us do the following. There is a very, very, very important command in Linux, which is called strace. Strace allows you to see all system calls, which an executable does when it runs. By the way, the term system call we were using already very often. So what is a system call? Let us discuss it first, and then we would examine the sequence of system calls. System call or syscall.
It is the call to the kernel, one of the predefined kernel calls.
Yes. A system call is a call to the kernel via the kernel API. For a very long time, making system calls was the only way of how a user level program could interact with the kernel. So if you want the kernel to perform some action for you, or you want to get some information from the kernel, this is done through the corresponding system calls. In modern day Linux, system calls are not the only way of communicating with the kernel. There are other ways. And to some extent they are sometimes better, sometimes not. Let's see. What am I trying to do? Okay, I'm trying to stop sharing and get back to my whiteboard. User level, kernel level communications. In Linux, that is. One of them, and still the primary one, the most important one, is, yes, syscalls. Syscalls. We must explain precisely what a syscall is. What do you think? Is a system call something like a function call? For example, you write your C function, C program, it calls, for example, it calls exit, as we discussed above. So is exit very much like a function call, similar to your application level functions, subroutines, or whatever, how you call them?
From the point of programmer, it is kind of similar because we are using some of libraries that provide function interface to the system calls.
Yes, but this function interface to the system calls is very, 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 very thin. This is provided by the library, which is called typically glibc on Linux. So basically, it looks like this. So that is your application. This is your application. And although it looks strange for you, but you will see now why that. This application can make calls to the glibc library. G stands for GNU. This is GNU libc library, which is the main C library, standard C library for the C programming language under Linux operating system. As far as I understand, the BSD family has its own libc implementation, which is not glibc. There are several libc implementations. Cygwin uses yet another one, so glibc is not the only one. So this is your C, for example, application level program. It can call glibc. Glibc would, if necessary, not necessarily, but often, subsequently make kernel calls. Or you can make a kernel call directly. How, for example, by incorporating the corresponding assembly level piece of code, which would make a kernel call. So, for example, you are probably familiar with the call malloc. What does malloc do?
Allocates some continuous piece of memory and returns the pointer to it.
Yes. In your program, when it runs, there is a memory area which is called heap. And actually, heap is a part of your data segment. So malloc takes some memory from the heap. Heap has some internal structured organization, so you know how to take a memory block from the heap and how eventually by using free, you would be able to release memory into the heap. So fine. Malloc allocates memory from the heap. Is malloc a glibc call or a glibc call followed by a kernel call or just a kernel call? So what is it? Malloc is a libc call. So basically, if there is enough free space in your heap, then there is no need to get the kernel involved at all. That should be pretty clear. Why should we involve the kernel if we can organize the data structures in our heap at our user level, at the application level, get a free block of memory, return the pointer to it to the caller, and then when it doesn't need to use it anymore, it executes free and the corresponding block of memory is returned to the heap. So by itself, malloc is a libc call. A problem with malloc occurs if heap is not long enough, is not large enough. In that case, we need to enlarge heap, and to enlarge heap, we probably need to enlarge the whole data segment of our program, right? Need to enlarge the data segment. And to enlarge the data segment, malloc internally, having seen that the data segment is not large enough to accommodate the request for more memory, it would make a kernel call. And do you know how this kernel call is called? That's, by the way, there was a question actually, what is going to appear in our exam? Definitely the timeline of operating system developments when a particular operating system was developed is not going to be in the exam. But it is one of the favorite examiner's questions, is which kernel call is behind malloc. You could get that it is malloc again or anything like that, not at all. A kernel call behind malloc is called sbreak. S-B-R-K, for historical reason. What break? S-break is probably some kind of system break. Why system break? In fact, it is a kernel call to change the size of a data segment. So typically, for example, what would happen is that our C++ program, if it is C, it would call malloc. If it is C++, it would call new first. New internally would call malloc. And if not enough memory, then malloc would call sbreak. Either as yet another function within glibc, and that would eventually make a kernel call, or maybe by making a kernel call directly. Or obviously, it is possible that our application level program may call sbreak directly, but this is very, very seldom needed, and it is a bad practice, actually. Eventually, when it comes to making a kernel call, it is not like, well, okay, a normal function call. How a normal function call works in our C++. Just without the precise details, but in general, how would it look like when we call a function? So what happens?
We're allocating place on the stack and going through initialization process and loading arguments, and then proceeding with the code of the function itself.
Generally, yes. So what happens is that there are many ways of how this could be done. There is another part of the data segment which is called stack. But both of them are part of the data segment of your process. And stack grows typically in Linux systems, stack grows from higher to lower addresses, but it doesn't really matter. So this is already a used part of the stack. In order to make a call, we first of all, it depends on the calling convention. There are multiple calling conventions. I'm not discussing the details. You put the arguments on the stack, then you put the return address on the stack, and then you do an instruction which basically jumps to the address of the callee of the function which you call. And that function already knows that the first item on the stack currently is the return address. Let's preserve it. But the previous items are parameters. Because each function has its own signature, it knows how many parameters it is required, so it would use the previous data items with the corresponding lengths on the stack in order to extract the parameters. And when it is done, it would, depending on how it is organized, it would take the return address, load it into one of the registers, clear the stack. Actually, this part of the stack unwind it. It could be done either by caller or the callee. It depends on the calling convention. I deliberately skip this detail at the moment, and then jump back to the address previously memorized on the stack. So that the call and return from the call. So basically, a normal function call is just pushing something on the stack, jumping to a particular address, and then returning to the address previously memorized on the stack. Kernel calls, when it really comes to crossing the kernel and the user space boundary, this kernel user space boundary, glibc is still in the user space, but then calls occur right into the kernel. This is nothing compared to that. Kernel calls are interrupts. We did not discuss yet a very, very important notion of interrupts. We'll maybe start discussing it if we have time today. If we don't have time, then later on. But the idea is we make an interrupt which completely disrupt the normal sequencing of instructions inside our application, and results in a so-called interrupt handler, which is a part of the kernel to be invoked. This is a very critical mechanism why we do kernel calls, why interrupts. We may store the parameters required for this call somewhere. Typically, they are stored in either in the registers or in a data area, and the address of that data area is put into one of the registers, typically not on stack, because when we perform an interrupt, then we eventually get this interrupt processed by the kernel, and we're on a completely different stack then. So the original stack, although it can be found, but it is difficult to find it. Whereas registers are still available, and it is much easier to get the rest of your parameters through the registers. So the question is, some of you know quite a lot about hardware architecture. So why do we perform kernel calls? Why interrupts rather than in a normal way like function calls?
Excuse me, can you please repeat what the critical part again? I didn't quite understand it.
The critical part is precisely that a kernel call is made via an interrupt. Interrupt means when you make an interrupt generating instruction. So for example, and that was your application. The application was developing, so you execute instructions, certain instructions in your application code. But then there is an interrupt instruction. An interrupt instruction, it is not even like a jump. If your instruction is jump, then you jump to another address and you continue from that address on. But interrupt means that
is to give a higher priority to any ongoing running task.
It means that your current running sequence is indeed completely interrupted. Interrupt comes with a certain number. So for example, interrupt n. And then interrupts are mechanisms which are built into your CPU. These mechanisms are hardware supported. So when an interrupt n occurs, the processor starts behaving in the following way. Somewhere in the low memory, so if this is a memory of your of your computer from address 0 to 128 gigabytes of memory, for example. That's your physical memory. In the initial area of your memory, there is a so-called interrupt table. When an interrupt occurs, then this interrupt table has entries. What entries are, we'll see in a second, for all those interrupt numbers. So there is a corresponding entry for the interrupt n, which we deliberately caused. There are many reasons how an interrupt may occur. For example, if you perform a division by 0, integer division by 0, it is an interrupt. By the way, what if you perform a floating point division by 0? Do you know? So, for example, what is the difference in C? Int I equals to 0, int j equals to 1, int k equals to, you guess what, j over I. What happens in this case?
It will produce an error.
An error, but this is not just an error, it is an interrupt. Interrupt happens. And this interrupt has a corresponding number, interrupt with some number. The code name for this interrupt is obviously zero division, all right? And suppose that it is here. So again, an interrupt happens and control is passed to, well, to where the control is passed, we'll see in a second. So an interrupt happens, and this interrupt has the corresponding entry in the interrupt table. That's what I would like to say. If, however, these are floating point numbers, so for example, double I equals to 0.0, double J equals to 1.0, double K equals to J divided by I, but now it is a floating point division, then no error and no interrupt occurs. The result is simply infinity. In floating point arithmetic of our Intel and other CPUs, there is such a thing as infinity. So in this case, 1 divided by 0 is perfectly okay, it is infinity. For floating point numbers, not for integers. For integers, it is an interrupt. Other interrupts may occur as a result of other errors. They, as we know, can be caused deliberately when we simply execute the interrupt instruction with the argument being the name of this interrupt, or, very importantly, interrupts can be caused by external devices. We'll come to this point later. This is very, very important. Interrupts can be caused by external devices. In any case, when an interrupt of whatever reason occurs due to an error, or being a deliberate interrupt caused by an interrupt instruction, or an interrupt from an external device, this interrupt has a number. And then the processor automatically looks up the interrupt table, which is stored at the beginning of the memory, and corresponding to this interrupt number, extracts, let's say, a 64-bit address from this interrupt table, and then passes control to this address. That's how we can invoke kernel functionality through an interrupt. So the question is, why do we do it in such a complicated way? rather than just calling the corresponding address in a normal way, like we call functions, subroutines, methods, and so on. The reason is, when we invoke a certain functionality via an interrupt, it is executed in the kernel mode rather than in the user mode. There are, well, at least two, although in fact four different modes in the Intel CPU, in the Intel family of processors. The two intermediate ones are rarely used, although from recently, especially with the advent of virtualization, the Linux kernel started using them as well. But for now, let's say that there are two modes. There is a user mode, which is unprivileged, and there is a kernel mode, which is privileged. Privileged means there are many differences between these two modes. In particular, in the user mode, unprivileged, you can see only the memory within your own memory map, within your own virtual memory allocation. So basically, a process had a memory allocated for it, and it can only see its memory. So whatever address it uses, it would only point within that that memory segment, which was allocated for itself, or it would be invalid. Whereas in the kernel mode, you can see the full memory which belongs to all processes. That's number one. Number two, in the privileged kernel mode, the CPU physically, mechanically, it is how the hardware design is done, by hardware design, is allowed to execute instructions, some instructions, which are not allowed in the user mode. So, for example, some instructions related to input-output control. These are two principal differences. Full memory view, including the address spaces of other processes, and also being able to manipulate those memory maps, and being able to execute privileged instructions. Because kernel services, which we require, very often indeed uh, require execution of privileged instructions, for example, then we can't make kernel calls in a user mode unprivileged simply by a kind of function call. We really need to do it via an interrupt, and if we do it via an interrupt, we also switch ourselves into the kernel mode. We give control to the kernel, and it is executed in the kernel mode. So that's what is very important to understand about interrupts at the moment. I think our time is almost over. I will answer questions, and we will continue next Friday from this point on.
Can you please put the links of the Sketchpad and Sketchpad files and also the recordings in the Moodle?
Oh yes. So as I promised, so after that I will do it in Moodle. Yes. And what you say scheduling? You mean syllabus, right?
No, Scratchpad. This
Scratchpad, yes, of course. I will immediately after our lecture. I will post them both actually to our Telegram channel and Moodle. Please pay attention first of all to our Telegram channel. It will be more rapidly up to date than Moodle. So I normally do almost all communications via Telegram, but later on it's Moodle as well. Okay.
Okay.
Telegram is our best friend. Moodle is only our supervisor, but not a friend. Okay. Thank you. So we are done for today. You see, explaining all these concepts took a little bit more time. We'll still need to talk a little bit about interrupts, but then we will be ready to examine the Linux kernel in detail, as I promised. We'll reconfigure and recompile Linux kernel. Not today, unfortunately, unless you want yet another lecture in the evening, but we'll defer it until Friday.
Okay, thank you.
Thank you.
Okay,
Thank you. Have a good
Thank you. Goodbye.
Bye.
thank you. Goodbye.